we are talking about on-off appliances, and a good example is a regular incandescent or maybe CFL bulb. On top of that, there are appliances that could be called multi-state. For example, if you have a fan with different settings like low, medium and high, then we have a multi-state appliance. The last type of appliances is very difficult to disaggregate. Unfortunately, we have more and more appliances each year that fall into this category. The power tool is just an example of such appliances. The whole idea is that the power can change gradually, not as drastically as in this case, and that will be very difficult to detect. Now, what are the significant components of any ARM system? We need to have a data acquisition system to get the data from the mains. Then we need to characterize appliances, and those appliances are characterized by their features. Some people use the term signature, so we can talk about signatures. Then we need to apply the disaggregation algorithm, and finally we need to provide some sort of feedback to the homeowner or to whatever application we need this ARM for. There are many ways to categorize ARM methods. For example, on the first international workshop held at Carnegie Mellon University approximately 2 years ago, the new methods were classified as events-based and eventless disaggregation. We, however, prefer this way of classification based on the hardware used. If we recall that one of the major drivers for ARM is introduction of smart grid and smart meters, then we need to consider very special algorithms suitable for this hardware, because we cannot get any sort of waveform information. If we want to use more expensive hardware that also needs to be installed, then we can talk about usage of waveform, current waveform, for example. Thus we can potentially get better classification. So based on this categorization, we will talk about two different approaches to ARM. Now, ARM by itself is intended for homeowners in the majority. So what the requirements could be for the homeowner? We actually conducted several surveys. The problem here is that if you're talking about energy saving applications, you have to understand that only households that are interested in energy saving would use this technology. And the fraction of people who are interested in energy saving, at least in the US, is very small. We are talking about 8 to 10% of the overall population. In Europe it is probably more than that, but in the US it is pretty small fraction. So because of that, we need to survey people who are interested in energy saving. First thing down here is that the ARM system needs to automatically detect and classify the major end users in a household. What does it mean? Is that once the system is running and it works, it will tell the homeowner which particular end users are available in his or her household. Then, once those end users are found, we need to accurately detect their presence in time, including also the power draw. This is the next item here. On top of that, we need to maintain data privacy and security. Why is it important? Mainly because the behavior information can be extracted from the smart meter, and if this information is available to a third party, then there would be loss of privacy. Now, about the rate, how frequently the disaggregated information need to be updated. If you're talking about energy-related applications, this people actually don't need to get real-time information, even though it is it's looking a little bit surprising for some people. If you're talking about demand response application, that needs to be a little bit more frequently updated. For fault detection and diagnostics, we're talking about such appliances as HVAC, for example, then the information needs to be updated near real time. The same as for health and security applications. Okay, now that there was some sort of background, let's briefly review some basic methods. And because, as I just mentioned, there are about 100 papers on this subject per year recently. There are very many different methods, and the particular methods that I selected for this tutorial are those that have practical importance. That is, as soon as you see any sort of a method, you also see a commercial developer or commercial product. So, this is considered to be a classic method, and it culminated in a commercial product which is called SPEED. It requires professional sensor installation, that is, a professional electrician needs to put something on top of a regular meter, and it has a sampling rate of about 20 kilohertz. So this is not the smart meter. Now, how it works? If we look at the left-hand side picture, this is a little bit more realistic picture as considered as compared to that shown on one of the first slides, if you remember. So we no longer see here nice and easily identifiable appliances or rectangular shapes. The method works as follows. First, they use a software edge detector to identify changes in the steady-state power draw. Then there is a cluster analysis algorithm that is used to locate these changes in two-dimensional signature space. Why it is two-dimensional? Because you have both real power and reactive power. For appliances that have only resistance, like incandescent lights, you see these clusters, they are for the lights. They don't have any reactive component, but other appliances, especially those that have motors, they have significant reactive power. Once the clusters are identified, positive and negative clusters of similar magnitude are paired or matched, and in the fourth step, known as anomaly resolution, unmatched clusters and events are paired or associated with existing or new clusters according to a maximum likelihood algorithm. In the fifth and final step, pair of clusters are associated with known power consumption, so that each individual end-use load could be tracked continuously in time. So this method easily detects nice on and off appliances. It has some troubles with other appliance types, and it has some other drawbacks that we will consider further. Now, a little bit about the problems of this method. If you recall, this is an idealized picture of Neon shown on one of the first slides. One of the characteristics of this idealized picture is that the power draw is essentially a delta function. It doesn't have any spread. In reality, however, if you're talking about a coffee maker, and this was a representation of a coffee maker, then actual distribution of power draw for the coffee maker is pretty wide. If you have downloaded the presentation file, you can magnify or zoom this particular picture, and you will see that the range here comes from approximately 360 watts all the way to 620. So this is tremendously wide distribution, and this is unfortunately typical. For the waveform, unfortunately it is also not very smooth and simple. The picture that you see here, it is from a paper, and this waveform is of an air conditioner. Seems to be a very nice distinctive and pretty much distinctive waveform. Unfortunately, in real life, it is not always so. What you can see here is a waveform of a CFL light, and the CFL bulb was connected to 8 other devices on the same circuit. So, depending on what was on and what was off for a given CFL bulb, the waveform could be pretty much different. Different colors here designate different times at which the waveform was taken. You see the variations here is huge, and it may not be simple to remove it by some sort of hardware. If you're looking about this method in general, you need to detect changes of power or detection of events. This is not very straightforward. It is because we have interplay between good detection and too much noise. Another obvious challenge is characterization of variable loads. But those variable loads are probably more seen if we consider more recent appliances. Here is an example of such recent disturbing appliance, which is called HRV, heat recovery ventilator. Alright, if we look at the power draw pattern of this appliance, it is very wild, and it would be extremely difficult to disaggregate any other signal if this appliance is working. Fortunately, for the time being, these appliances are not widely spread, but still there's a problem. So, if you're talking about this particular method, we can use some sort of grading. Of course, this grading is subjective, and it takes into account whether the system can identify appliances automatically, which is usually very difficult because of the lack of good signatures, and then continuously disaggregate those induces in the data stream. So, you see here one sort of induces that is much easier to be dealt with. This is domestic hot water. It has very distinctive way of power consumption. All other uses, usually they have problems with automatic recognition. This is why we have somewhat lower quality. And if you return back to the minimum customer requirements, we certainly can see place for improvement. Now, because this method works only with events, that is with ages, it doesn't require too much computational power. We are processing only changes of power. So this is why it is relatively easy to deduce algorithms that are not computationally intensive. Now, let us try to improve this basic method, and in attempt to do so, was undertaken in UK, University of Oxford, Professor Malcolm McClure. Now, there are not too much publicly available papers about this particular research, mainly because commercial entity called Navetas was almost immediately founded, and I believe it is in place. It has been in place for about 5 years now. Current status is field trials, and we will see relatively many such current status for other technologies as well. The whole idea is to use time-related features together with the power-related features to try to improve performance. It is still based on a dedicated sensor that can sample with approximately 20 kilohertz sampling rate, current and voltage. So there is some guesswork in explanation of how this method works. This dissertation very well explains numerous aspects of this method. So they take into account duration of time on, duration and the time of day features, meaning that, for example, activity related to kitchen breakfast preparation should be shown in the approximately breakfast time, and activities related to some other distinctive appliances can also be easily identified. They used Bayesian belief network for the classification that tries to take into account all available data. And the time-related features, they make it easier thematic identification and disaggregation accuracy. Some other challenges still there. So, if you would like to somehow upgrade this system, you have significant improvement as compared to the basic method. There are obvious problems for lighting and consumer electronics. Why? Because the amount of power per switch is relatively low for both lighting and consumer electronics. And there are some other issues related to these particular two induces. Customer requirements are probably better satisfied with this system because we have relatively heavy computational algorithm. Might be a problem of frequent updates. Now let us talk about the noisiest method. Noisy is twofold here. First, because the method is based on the high frequency electric noise that propagates through power line. And second, because there was a lot of noise about this method when Patel and his co-authors published the first paper. It was published in 2007, 6 years ago. So how it works? The whole idea is that many electrical appliances, particularly consumer electronics, when they are connected to power socket, they generate a specific electric noise in the whole power line. So if we connect the sensor with high sampling frequency to another socket in the same household, we would be able to see this noise. This is how approximately the picture from the sensor would look like. You have a baseline noise that shows some peaks for the appliances that are already in place. If you turn on another appliance, you will have additional peaks that could be characterized and used for identification of appliances. That would certainly help in appliance identification. This approach was undertaken by a large commercial entity, Belkin. All right, and it is not very smoothly propagating yet because there are several challenges that need to be overcome. For example, power line communication. If you're talking about individual households, like individual house, this is one thing. If you're talking about multi-family building with numerous apartments, it would be a little bit different thing. Power draw still requires a dedicated sensor to be installed on the mains. We have tremendous improvements for the consumer electronics. It is not surprising because we are using characteristic features related to consumer electronics there. One problem with this particular approach is that the data need to be compared with those that are being kept on the cloud. So because of that, there are some problems with data privacy and security. This is a reminder of various methods that are being used for disaggregation. So we talked for the time being about those methods that require hardware installation. Let us now talk a little bit about methods appropriate for the smart meters. In terms of disaggregation technology, what is being used is basically the same approach. It related back to the original MIT methods. It is somewhat truncated in the sense that we no longer have reactive power or harmonics. We have only real power sampled at 1 Hz or sometimes even with lower frequency. Commercial products are already available, even though they are free for the time being for the homeowners. The homeowner, however, needs to surrender the data privacy with the use of those products. And for the time being, because they are supposed to rely on the existing sensors, like a smart meter or dedicated home energy display, only software based. Because the information available from relatively low sampling frequency is not as rich as that from high sampling frequency, the expected accuracy and other characteristics should be worse. However, the opportunities here are much better. For example, the cost and the complicated sensor installation, they have been found to be the two most important barriers for the home energy management technology. And here what we see is a specific device which can essentially cost about $10 a piece with the incentives from utilities. This device can talk to a household smart meter. Moreover, last year the IEEE organization accepted a new Smart Energy Profile Standard version 2, and this version essentially allows to use additional internet technology for communication. So these opportunities can make low frequency neon to be more attractive from business point of view. What we can see here is a snapshot from one of the vendors. This is a plot part, and this snapshot actually shows what a homeowner would see if he or she uses this technology. As you can see here, the reliably detectable end uses for the time being HVAC, refrigerators and dryers. this majority of devices here are such exotic power draw as electric vehicle charging that I believe majority of people don't have yet. Always on, which is not very informative for other. So the technological ability is very low here. And we have to recall that home energy displays that they are usually based on clamp on sensor. This is how it looks like. The whole construction needs to be connected to household mains. So just by merely looking at this picture, you can probably understand that the data quality will be relatively poor. Of course, this gradient is pretty much subjective and comparative. Of course, the abilities here are much worse for the time being, again, especially for lighting and consumer electronics. And if you recall the original requirements of potential customers, we have problems in almost every aspect here. One especially important aspect is data privacy and security. The customers, to get free software, need to surrender their data, and I guess the business model of these companies is to try to reduce useful information for appliance manufacturers. There have been numerous publications in this low frequency field, many from academia. This particular paper has been cited often, so this is why it was selected. The disaggregation here is not event-based, which means that not a small fraction of data, but all the data need to be processed. We have here some specific Markov models, and the effect of these models is that the distributions of time on and time off are indirectly accounted for. And the disaggregation accuracy is improved over the previous method, and approximately it reached the disaggregation accuracy of the basic neural method that implements a dedicated sensor for that. However, has a couple of severe limitations here. It is the most severe limitations are two. First, we need to know the number of appliances in order to use this model. And second, the computational complexity is exponential with the number of appliances. Let us have a sort of summary for the state of the art. Why the commercialization is so low? This peak for interest to this technology, it probably started 5 years ago with such major companies as Google and Microsoft essentially providing homeowners' ability to see the energy consumption online. What are the problems? The first problem is that everything works finally in the lab, everything works finally in employee home, but in field trials there are problems. Why is that? First of all, there are unconsidered appliances. It is very difficult to have a good spectrum of appliances well represented in the lab. And to be well represented, possible faults of those appliances also need to be somehow modeled. This is very difficult. Another thing is unpredictable appliance and behaviors of the users. This is the other thing that is very difficult to predict. If people are using several appliances all together and switch them on off all the time, it's very difficult. Second problem, second challenge here is how to characterize accuracy. F measure, this is something that is coming from the pattern recognition field. People in energy-related research usually prefer to talk about the percentage of energy that is explained in terms of the disaggregated appliances. We can also talk about receiver operator curve, ROC, and there could be some other measures. It is still not an acceptable metrics. The other challenge related to accuracy is how to get the ground truth. It is, first of all, there are no commercially available off-the-shelf system suitable for residential sub-metering that would be cost-effective and that could be used for ground truth of every appliance. There is some work that is done at Carnegie Mellon University by Mario Berges and his students that are trying to use some different sensors to get ground truth, but still very difficult. And the third thing is that third-party validation is needed, but because of the challenges here, it's very difficult to do. There are some limited attempts from national labs and Electric Power Research Institute. They devised a couple of specially equipped households. But again, because it is difficult to reproduce various appliances and their combinations, it is difficult also to use for validation. There were some myths in this field that I would like to briefly talk about. The first myth was very popular in 2010, and it was believed that with a higher frequency sampling rate we can get better accuracy. The higher the rate, the better the accuracy. In reality, unfortunately, it is not a very simple relationship between one and the other. As we go with a higher sampling rate, we also increase mutual disturbance between appliances and noise. The other belief was that with relatively low sampling rate, we can still have meaningful disaggregation. Why is that? Because the ZigBee-equipped power meters, they usually send a signal about power consumption every 15 minutes, 4 times an hour. So let's take this 15 minutes data and try to disaggregate. In reality, it may not work well. Let's take a look at this picture, for example. This is electric range. What you can see on this picture that was taken with from data sampled every second is that we have a nice oscillation of power. You can consider this appliance as one of appliance. However, if we sample power consumption data every minute, we will get something like that. What is that? This is probably a variable power consumption, at least as it looks now, and it is extremely difficult to disaggregate that sort of a signal. Another myth that was available approximately 3 years ago and was very popular, it was the concept of power signature. So here, for example, got several offers from the industry, which all were based on that sort of approach. It is, all appliances are different, they all have signatures, let's get the signatures from, for example, employee households. Okay, and use some simple pattern recognition software. Thus you will get the disaggregation in place. In reality, the problem with the signatures is that many appliances actually don't have signatures. And the signatures of other appliances, they get very fuzzy. This is what we can see here again. Another thing, which is also, I believe, a myth, is one statement that the use of NIAUM will result in 20% energy saving. This can be true, but it can only be applicable to the households who are interested in energy saving. If the household is not interested, then you cannot get any sort of energy saving, whatever information you provide to the homeowner. So you need to remember that only about 10% of households are interested in energy saving. And the last thing here is people like to talk about smart appliances, and the need in NIAUM will diminish pretty soon. In reality, even if the smart appliances are coming, there is approximately 20 years of transient period when all the appliances still will be numerous, and this technology is going to survive. Okay, are there any questions so far? Okay, so let us jump ahead and talk a little bit our research in this field. Let us make a step back and return to the basic NIAUM method. What will happen if you have only real power? Let's look at this picture, and you see, if there is no reactive power available, everything that is included within this circle, they would overlap, and it would be extremely difficult to distinguish between, for example, a dehumidifier and water pump. Here we have a bunch of appliances that all overlap in power draw. Ice maker, lights. Here we have a fridge and electric bulb that consume approximately the same amount of energy. Also very difficult to disaggregate. So the major problem here, you would say, is the problem of the overlap. If you remember, there is an advanced method that takes into account additional features from the time domain, but those methods, they are computationally inefficient. They also have some modeling problems. So we need to overcome these two challenges. Our key idea for the computational efficiency, and we are still talking about on-off appliances mainly, let us order appliances by their power draw on average. So if this is appliance number I, for example, appliance that draws a little bit more power will be I plus 1. Appliance that draws less power will be I minus 1. And then let us see that actually there is no overlap between appliance I minus 2 here, right, and appliance I plus 2 here with appliance number I. This means let's take only an appliance and it's called as neighbors. For the time being, we are talking a tuplet of size 3. It is 1, 2, 3 appliances together. And let us disaggregate only these tuplets. In this way, we essentially decrease the number of appliances to just 3. Once we get the solution, we can fuse them together for different tuplets. This is a key idea in terms of computational efficiency. We can also consider for running missing data when we are talking about tuplets, if we properly address them in the possible transitions. For the overlap problem, we have both power and time-related features. Power features let us take not only the power draw, but also the so-called inrush current or power surge. It is characteristic for mainly motor-based appliances and also for some consumer electronics. The value of this surge could be used as an additional feature. Time on, time off statistics, I guess this is self-explanatory. Bottom line is that instead of a single dimension for our feature, which was only power change, now we have from 3 to 5 additional features that can be added together and thus improve the disaggregation quality. The last thing here is let us consider possible transitions within each tuplet and use analytical solution to characterize the probabilities. You see, what happens here is that instead of the known solution that tries to solve precise system with approximate methods, this way solves approximate system with precise solution. And the values, these formulas, they just need to be developed once, and then they are applicable to anything. Now, we need to still to decide who is who. It is the basic method proceeds with identification of clusters. So these clusters need to be somehow assigned to known end users. So the approach here is very simple. Let's use the statistical distributions relevant to each of the end users, and also use different household types. This is why we are talking about mixture distributions. Some of the end users here are relatively simple. Some are very complicated to get. For example, for lighting, you have different room types, and you have different bulb types, CFL, incandescent, halogen. There could be different number of bulbs in a fixture. You will see right now how it works. How to get distribution of power draw for the end use of lighting. Let us consider a specific type of a household, which is called single detached home. This is a typical household for the US. Then we have at least 7 different types of rooms within this household. Those rooms and their lighting characteristics, they have been characterized in numerous research works. So everything is known. For each type of room, we know what is the distribution of bulb types as per 2013, for example. We know how the number of bulbs in each fixture can be distributed, and so on. So bottom line, we can get that sort of characteristic power draw distribution for lighting. And you can see these peaks, they correspond to the fact that the wattage on each bulb, it comes in discrete different values. For example, you can have electric bulb of 40 watt, but you can't have 35 watt if it is an incandescent. Now, if you recall idealized picture on one of the first slides, I believe it is slide number 4, for the television, coffee maker and refrigerator. So the power draw of the television was considered to be constant there. In reality, it is not constant. For a CRT, we can get a picture like that. Why is it so noisy? Because there are frequent changes of brightness, and also we need to remember about the audio. For the LCD televisions, those variations are usually smaller. However, every time homeowner changes the channel, you will see a significant drop in power, something like that. So, and because usually this end use is confused with the lighting, we just need to be able to distinguish between these two. So let us use such fine feature as standard deviation, for example, of the signal between times on and off. For the consumer electronics, it will be relatively high. For the lighting, it will be very low. Now, how the whole method works? We need to get approximately 2 weeks of data. Once we have these 2 weeks of data, we can proceed exactly as in the basic method, that is to get clusters. Okay, you can see some clusters here. Each cluster, it is not, of course, Gaussian distribution, but we characterize the distributions by empirical methods, so that is better for us. Once we have found negative and positive changes of power that match each other, we can estimate preliminary time on and time off durations. And for each of these characteristics, we are using empirical distributions. Then, once we have all the distributions available, we can try to disaggregate by tuplets. We have a system which resembles first-order Markov chain here. In reality, it is not exactly first-order Markov model because there could be missed or foreign data, so that the state of the system at a given time corresponding to a power change may depend not only on the previous, but depend on several previous steps. So the solution for that is modified Viterbi algorithm. Then once we have run through all the tuplets, we will have better disaggregation than the initial one. Thus we can update cluster distributions and rerun the disaggregation algorithm once again. After that, we essentially need to classify the clusters, that is to say, who is who. And we'll see how it works. Now, when we estimate the clusters, we need to remember that each cluster would include some foreign data. So essentially the distributions of power, for example, in time, they would be mixed distributions. However, if you just do a very simple math for naive Bayesian classifier, we will see that the classifier that is based on mixed distribution work exactly with the same separation ability as with the Fourier distribution as soon as the fraction of the major distribution in a tuplet is larger than half. This is a very nice and useful feature. If you're talking about a block scheme, this is how it works. We collect 1 Hertz resolution real power data collected for about 2 weeks. And then we proceed with simple clustering algorithm. Alright, from it we get initial distributions of power and time. Then we use for the first time the disaggregation algorithm, get new distributions updated, and then we proceed once again with that. After that we will have updated distributions of power and time for each cluster. We can classify who is who. And after that, essentially, we can use this algorithm in near real time. Because this method includes several stages, we wanted to test it by several by its basic components. So the first thing that we needed to test is the most innovative part, which is the disaggregation algorithm by itself. So we tested it first, and the results were reported, I believe, in this conference a couple of years ago. So we wanted to use here publicly available data. Unfortunately, there are no good publicly available data. The REDD database that was used here, it suffers from several problems, like for example, data on the mains don't fit the data on the circuits. We will talk about this very soon. So for this testing, we just took individual data on individual circuits and aggregated them together. So we didn't have to implement any clustering algorithms. We just considered each circuit as an individual cluster. And we wanted to see what would be the disaggregation accuracy. Here the accuracy is measured by the F measure. I will show what it is a little bit later. And as an alternative approach, what was used is a Bayesian classifier. So we'll talk about that on the next slide. But here I would like to tell you that one of the challenges of the low frequency disaggregation, as we just saw earlier, was the overlap problem. Here we can see that indeed appliances number 4 and 5, they have a very heavy overlap. They consume approximately the same power, and if you take into account the standard deviations, you will see that the overlap is very heavy. Because of this overlap, if you use just Bayesian classifier, it is essentially a comparison of probability density function of power draw of each of the appliances, you will get very low separation ability here. If you use our algorithm, you can see it nicely overcomes this problem. Now, what is that F measure? If you have disaggregated signal from the algorithm, it is shown in red, and if you have a true signal, or let's say submitted signal, which is shown in blue. And if you want to forget about the value of the power draw, which is essentially measured by the y-axis, we can talk about true positive, which is the overlap between them in time. We can talk about false positive, which is essentially this length in time. And we can talk about false negatives, which is essentially here. Once we have these three values, we can calculate the F measure. In ideal case, it will be 100%. Now, let us talk about the other portion of the algorithm, which is the whole solution. For this purpose, we collected numerous data ourselves on individual end users, and we also added some additional data from the open data. The approach was just to characterize each individual data set with statistical characteristics and use our classifier to which end user it will classify the given data set. Alright, so we can see relatively nice who identification results here. Alright, for public data it is a little bit worse. The major problem, as is expected, would be for lighting and consumer electronics, but if you use the fine features, the accuracy here is pretty nice. If we want to make the task a little bit more realistic and more complicated, let us aggregate those found end users together, make synthetic data and try to build clusters and use cluster characteristics to classify. Then, of course, Of course, here would be worse than in the previous case, as you can see, but still about 80%. Now, the another thing is to have a sort of field testing. And I can tell you that usually in new publications, the best case, what is used for field testing is the own household of the researcher. This is in the best case because more often than not what is used is simulated data or publicly available data, which is problematic as you could see. In our case, we wanted to use data from real households that were willing to participate in energy saving experiments. So we selected a large luxury apartment complex in our suburb, the so-called Silver Small Apartments, and we wanted that each household would have a range of distinctive appliances applicable to our end users. And we used two different systems for data acquisition, both off the shelf. That is, if you see a paper on this technology, most likely they will use the same off the shelf metering system. I don't disclose which one because both perform pretty poorly, as you will see. One is connected to the mains and records data every second. The other is connected to both mains and to individual circuits and records data every minute. And both required professional installations. The first thing that we discovered were data acquisition problems. Missing data, what it means is that the data simply are not recorded. And by the way, both commercial quantities that both commercial firms that work in low frequency disaggregation, they both complained on this type of data problem, missing data. Second problem is that there is inconsistency between high frequency sampling with 1 second resolution and lower frequency sampling with just 1 minute resolution. What you can see on these two figures is that essentially the data collected at 1 minute resolution is somehow richer than the data collected with 1 second resolution. Yeah, it's very weird, but this is the reality. That is, the major conclusion would be we need to use our own sensors. Right? Now, if we are talking about the system that records data every minute, unfortunately it also has unpredictable problems. There is a huge discrepancy between the power recorded on a circuit and the power recorded on the mains. So probably the battery is dead on the laser pointer. I know it's working still. What we can see here is the difference more than 200%. All right. In this case, the mains shows much 3 times higher power draw. All right, and this is for a range, so there is no any reactive component. The other picture shows the exactly opposite problem. So here, the power draw, this is the refrigerator. So the power draw of the refrigerator is seen on the submetering approximately 2 times more than that on the mains. And we have 5 different apartments. There were no any systematic way to predict a priori what will happen and what sort of discrepancy will be observed. So, because of this hurdle, the only way to have ground truth for disaggregation would be to use the F measure that doesn't account for the value of power draw, but only for the overlap in time. Now, because the signal collected at 1 Hz resolution was so poor, we had to work with the 1 minute resolution signal. And we have 2 problems because of that. You see, this is the problem that happens to the electric oven and electric range. It is constructed in such a way that to regulate the temperature on the range, the user essentially changes the relationship between time on and time off. For example, here we have approximately 15 seconds on, then about half a minute off. And this is approximately low setting. If you want to increase the temperature of the range, then the heating time will increase, but not the power. Now, what happens with this nice picture if you transition to 1 minute resolution in this wild, very wild power consumption pattern? It is no longer on-off. That is, it can be considered as on-off, but with such huge oscillations that it will be very difficult to get meaningful information. The same thing is applicable to electric dryer. As you can see, if we can sample every second, that's fine. We can talk about on-off appliance for the heating element on top of the motor that essentially circulates the dryer. If you have only 1 minute resolution data available, this is no longer as nice, because it's very difficult to say what sort of appliance is this. So these 2 problems would contribute to relatively low accuracy level of our algorithm. Now, this is a reminder of the block scheme of how we need to work. We don't have 1 Hz resolution data here, we have only 1 minute resolution data. But the reminder is essentially the same. We want you to see how it will work even with 1 minute resolution data. The first thing was to get clusters out of a period of time. Alright, here we use all 6 weeks of data that was available, and we got 10 clusters for the power changes. Some of those clusters were classified exactly as the ground truth that we had. Some were classified as lighting, for example, but for lighting we did not have a specific submitter, and so we could not tell whether it is indeed lighting or not. Some of them were either empty or unspecified. Unspecified is happens when the classifier doesn't know that there is no winner, clear winner within the end user that we have considered so far. It could, for example, correspond to some rarely used kitchen appliance. Bottom line, the 5 most important appliances is applicable to those households. They all were correctly identified. If you go back, you can see that those are electric appliances that were available in the households. HVAC, electric range, electric dryer, microwave, and refrigerator. 5. And all those were found correctly even with 1 minute resolution data, which is nice. Now, if you just take those clusters without disaggregation algorithm applied and try to find out how accurate this was, of course the results would not be good. For the best and easily classifiable end users. Refrigerator and HVAC, we have about 60% accuracy. Some components of this low accuracy can be attributed to the F measure. You see, for the HVAC system, usually we have relatively high power draw. Alright. Sometimes the power draw is very small. F measure does not account for that. If you don't detect the small power draws, it will negatively affect the accuracy. Now, if we apply the whole algorithm, it is the aggregation algorithm applied after the clustering, then the features were re-characterized, and then the aggregation was repeated, then we'll have that sort of accuracy data. We have nice data for HVAC and refrigerator here. For the microwave, this is a different story. For electric dryer and electric range, we have low accuracy exactly because of these two problems. They are no longer enough appliances. And we have to recall that we use F measure that only accounts for time, not for the power. So it's not surprising that we have low numbers here. For the microwave, somehow the consumption pattern from a microwave, it was also very strange. We don't know right now whether it was a true pattern of microwave or it is an artifact related to the sensor. If you look how the disaggregation accuracy evolves from the beginning of the method to the end, it's relatively, it can be seen on this picture. We can see that the number of identified and correctly classified events indeed have grown drastically for this particular period of time. So this is more or less nice. And this is relatively not very common results. And the main conclusion here is that we need to use our own data acquisition system, preferably based on a smart meter, because of the built-in accuracy, in order to run all sorts of field trials. Which also means that whenever you see that people are reporting about disaggregation using off-the-shelf electric power monitors, you have to take the results with a grain of salt because of this strange and unexplained behavior of the sensors. So let me finish on a more or less optimistic note. The major improvement here, I will say, is data privacy and security, because we don't need to get signatures and compare them with what you have on the cloud. All the signatures are essentially included in the software by the way of statistical distributions. And because of relatively low computational complexity, the disaggregation could occur in almost real time. This, I can tell you that the data collected with 1 Hz resolution, the data that was shown in one of the previous slides, the data from 9 appliances collected over 26 days. It was processed by a MATLAB algorithm during 3 minutes of computational time. So we can easily talk about real-time disaggregation here. Accurate power consumption is difficult to say right now. Now, why it is more optimistic than pessimistic here? Mainly because we were able to do testing separately. This before this field trial that was not very successful because of the sensors. So this is more or less the information that I have so far. If you have questions, you can discuss them. We have about 20 minutes remaining.
Just out of curiosity, when you were doing your sub-meters, were you sub-metering an individual electrical outlet or an individual appliance or an individual circuit breaker? Acknowledging that it didn't seem to work that well, what was your goal there?
Okay, you see it is much of a problem here to get ground truth. It is the sensors that are available on the shelf, they are applicable circuit breaker level. That is, electrician needs to connect each clamp-on sensor. Let me try to find the picture of the clamp-on sensor so that you understand what it is.
It's clamp-on, right?
Yeah, clamp-on sensor.
Then the next question would be, wouldn't it be helpful if you could measure individual appliances?
Of course. So here there are three, let's say, opportunities. One is LBNL, together with University of Berkeley, they developed relatively inexpensive plug-on sensors that can also use wireless internet to upload individual plug data. Unfortunately, those sensors are not for sale, and they had some problems. We worked with these sensors in the past on a separate project. They are not very reliable. Right now, I know that Mario Berges of Carnegie Mellon University is working on a different type of sensors that would use additional information, for example, acoustic information and some else, so that such appliances as, for example, washing machine, when they are working, they can be identified. So submetering is really a challenge. You actually need to submit on every individual appliance, which is difficult.
Well, I was wondering if you could maybe sub-meter the big appliance.
Yeah.
Maybe like the top 5. Maybe that would like...
Yeah, you're right. And this is the whole idea of using end users rather than individual appliances. Unfortunately, again, that is, we need to transition to industrial applications probably, because for industrial energy management and energy monitoring, there are sensors for submetering available, and these sensors, they have accuracy information available as well. So the systems that we had to try, they don't have any accuracy information, neither any obligations. So this is why they sold so strange information. But for industrial applications, there are some off-the-shelf solutions based on which custom solution for residential could be obtained. Generally speaking, it is a problem.
Well, yeah. Okay, on slide 44.
Questions are interesting.
Yeah, on slide 44. Yeah. Why were you clustering negative power changes?
The problem with the positive and negative power changes is that for some appliances there is a power surge.
Oh, right, okay.
Yeah, this is one thing. Another thing is that several appliances, they have distinct different positive and negative power change. For example, refrigerator, even if we remove the power spike corresponding to the inrush current, the power draw at positive power change when we turn it on, it is by 5 to 10% larger than when it goes down. So it is just, but it is not our invention. It was what suggested in the original work by George Hart. And there are some additional know-hows. For example, we need to account for voltage variation as well. And there is a nice normalization how to normalize power with regard to fluctuations of the voltage. This.
Well, and that's becoming more difficult with switch-mode power supply, right? And they also have, switch-mode power supplies also have inrush current, significant inrush current.
Yeah, that is, many consumer electronic devices, they indeed have this inrush current, but the problem here is related to the frequency of our sensor. It is, if it is measured every minute, for example, it will not be seen. It will just move out. Yeah, this is here. For this particular method, I can tell you that the latest information I have, it was a demo from Belkin. They installed new power meters, and the disaggregated information supplied to homeowners in terms of monthly bills. So every month the homeowner would get a highly detailed bill with every found appliance characterized by amount of kilowatt hours or just money that it's consumed.
Have you evaluated or considered into the set of rules for the disaggregation algorithm the active occupation profile of the applicant? Is it used to discriminate which appliances are running certain hours?
Yeah, this is what people in Navetas, I believe, are doing. Let's return back here. Now this is basic. Let me find, yes. So people there, they try to establish, let's say, schedule, typical schedule of households. At which time, which appliances are usually on, and which time they are usually off. So, and that this information was characterized statistically. It is not exactly 100% on or 0% on. They had some statistical profiles. And these profiles, they entered to the Bayesian belief network as additional input. So this probably allows to improve the accuracy. In principle, everyone can do the same. The problem here is that if, let's say, 90% of households would be nice, then 10% would have unusual profiles, so it would be difficult. Oh, sure. You have another question?
As an end user, what actions can I take with this information provided by your method? Should I buy a new appliance or?
You mean what applications are?
Yeah, of your method. As an user of appliances.
Okay, well, let's take a look on a specific slide for that. If I remember where it is located. Don't always remember. Okay, so if you're talking about energy, saving potential, people usually don't know how much energy appliance consumes. In good old times, if you buy an appliance, you will see what is the wattage of this appliance. Now you buy a mixer, you see it consumes 200 watts. Then you know it consumes 200 watts. Now you buy a refrigerator. In the US, it will show you approximate power consumption, not in kilowatt hours, but in dollars. So go translate it to power consumption. Also, not all appliances that exit factory will continue with the factory-defined power draw. It is a good refrigerator nowadays could consume 80 watts. Now, if it gets faulty, it can consume 800 watts. So this is the information that can be useful. And then, if you know how much your appliance consume, you can probably decide whether you want to use it or not. This is especially useful as soon as you have time of use electricity pricing. This is what inevitably will happen in many countries in order to better regulate the electricity consumption patterns with the smart grids. This we are talking about demand response here. Other things related to that, they are not so much related to the power consumption, but they are more related to behavior things. For example, if you see something unusual with how your appliances are being used, then probably it is a security problem or it is a health problem. So in principle, you can detect non-intrusively if there are some variations in the, for example, activities of daily living with the elderly. Or you can probably easily identify an intruder in your located home. And there could be some other, for example, I can tell you that a new US agency, which is called Informational IEEE, they were very much interested in detection of centrifuges. You see that this, some people can have a centrifuge at home, which is essentially a high-speed mixer. And whether they can use it for example, uranium enrichment. If smart meter data are available and they are pretty frequent for the sampling, then this can generally be detected by security agencies.